Welcome back. So we are going to be narrowing and focusing our idea or our concept of matter more towards a chemistry bent, thankfully, in that when we talk about matter, a pure substance, one of those types of pure substances were elements. And we found that, or we had defined that an element, the particle of an element, is that of the atom. So we're going to be looking at matter from a particulate level, just from with respect to looking at the elements. Now, the concept of the atom is a heady topic, and it has evolved significantly over millennia. Really, the idea of the atom as the smallest individual unit of matter has held sway for thousands of years. Even the great Greek philosophers postulated on the existence of the atom. And I would submit that those philosophers had a pretty enviable position because they were able to postulate on the idea of the atom, but they never had to prove anything. But you had to agree that it existed. Never had to prove it, well, because it's too small to see, but it's there. That's an enviable position. Now, with the advent of technological advances and experimental advances, experimental data, the idea of the atom began to take on more currency because it was supported by a table of data, if you will. Now, the first real example of fact-based or scientific-based ideas that could be backed up by experimental data was Dalton's atomic theory, and that was put forth by John Dalton in 1808. And there are four tenets to Dalton's atomic theory, some which mirror the admonitions of the great Greek philosophers and any other philosophers throughout time, and some that require leaning on actual scientific data. The first one, the first tenet of Dalton's atomic theory, is that an element is made up of atoms. So that's the declaration. All atoms of a different element are identical. Fair enough. Second, atoms cannot be destroyed or created. So that sort of goes into the law of conservation of mass a little bit. We know now that atoms can be destroyed through nuclear fission and so on, but that is really a very, very small consideration when talking about the idea of the atom, so that it is insignificant. So here now are examples of some expressions in Dalton's atomic theory based upon emerging scientific data. The third, all atoms of one element have the same mass. Atoms of two different elements have different masses. This was supportable by early nascent experimental evidence at the time. Lastly, atoms of different elements may combine in a ratio of small whole numbers to form compounds. Remember now, a compound is two or more atoms coming together in a specific ratio, and those atoms are held together by chemical bonds. One of the main ideas to come out of Dalton's atomic theory was the law of multiple proportions. The law of multiple proportions, which states that elements combine to form compounds, and this is the important part, in specific mass ratios. Ratios of masses, not absolute masses, but ratios of masses. Again, this was supportable by experimental evidence at the time, and when repeating numbers keep coming up, or specific mass ratios keep coming up in experimental data, it is something to notice, to take notice of. Here's just one example of that. We'll look at examples of two compounds of carbon and oxygen. So a further statement of the law of multiple proportions is that when two elements combine to form more than one compound, the different masses of one element that combine with the same weight of another element are in simple ratios of whole numbers. So let's take a look at this. If I had, say, a sample of carbon dioxide, and I took that sample and I decomposed it into its corresponding elements, carbon and oxygen, and I weighed those elements. For instance, in this sample, I'd have 3.46 grams of oxygen and 1.30 grams of carbon. And if I divide those numbers into one another in this fashion, I would come up with a ratio. In this case, this ratio is 2.66. Now, what this means is that any sample, large, small, if you will, of carbon dioxide, if decomposed into its constituent elements and those elements weighed and those masses divided into one another, we would come up with the same number over and over again. It is possible, and on that second tenet of the law of multiple proportions, that we can have carbon and oxygen as well coming together as a different compound. For this example is carbon monoxide. If I took a sample of carbon monoxide and decomposed it into its constituent elements and weighed them, in this case 1.73 grams of oxygen, 1.30 grams of carbon, I come up with a ratio of 1.33. 1.33. So this means that any sample of this pure substance, carbon monoxide, if I break it down into its constituent elements, weigh those elements and compare them as a ratio, it's always going to be this number. So we've looked at two examples where we can define a compound based upon its mass ratios. Further, we're able to look at two different compounds put together from the same elements and see that they are not the same based upon those mass ratios, or a couple of ways that the law of multiple proportions works. So let's get back to this concept of the atom, because that's really what this unit of study is all about. It turns out that the atom is not the smallest indivisible unit of matter, which has held sway for thousands of years. It turns out that atoms are built from smaller particles or parts known as subatomic particles. Subatomic particles, and we're going to find that there are three subatomic particles that we are going to be concerning ourselves with, and these three are given here. The first one in this table is the proton. The proton has a charge of +1, has an electrical charge of +1, and it's interesting. I think this is very telling. It gives the masses in kilograms of each of these subatomic particles. And look at this, on the order of 10 to the -27th kilograms. It's almost ridiculous to even express. It is ridiculous to express the mass of an atom or a molecule or a subatomic particle in a unit of measure such as kilograms, because it's such a vanishingly small number. We will eventually get around to looking at mass in another, perhaps more acceptable unit of mass, that of the atomic mass unit, or AMU. We're not going to be getting into defining that right now, but when you are in this type of mass, just again to take some license with this, we see that one subatomic particle, a proton, weighs about 1 atomic mass unit, or AMU. Again, I'll be using these atomic mass units here to compare the masses of these subatomic particles, but we will define that later. So we've established that our first subatomic particle is a proton, and it has a charge of +1, an electrical charge of +1, and it weighs about 1 atomic mass unit. The next subatomic particle is known as the neutron. The neutron is a subatomic particle within an atom. It weighs almost exactly the same as that of a proton, about 1 atomic mass unit, and it has no charge, 0. So it's not positive, it's not negative, it does not carry an electric charge. The last one, an electron. The electron subatomic particle. Notice here with respect to its mass, we're not defining what an atomic mass unit is, but rather we are doing a comparison of masses. Whereas a proton and a neutron weigh approximately the same, that of 1 atomic mass unit, an electron weighs about 1/10,000th, on the order of 1/10,000th the mass of a proton or a neutron. It is vanishingly small compared to a proton or a neutron. And more on that later, more importance on that later. We're going to find that importantly, the electron carries an electric charge as well, that of -1. So an electron has a -1 electric charge, a proton has a +1 electric charge, and a neutron has no electric charges. Now, an important consideration for 2 of the 3 subatomic particles, the ones that are charged. The protons have the positive charge, electrons have a negative charge. From a physical standpoint, these charged particles we find that opposite charges attract one another. Thus, a proton and an electron in general are attracted to one another. We have a positive charge on a proton, negative charge on an electron, and they tend to attract each other. Also, as we'll see, as they're packed together in an atom, if we have the same number of protons and the same number of electrons, which we'll find out that we do in an atom, that leads to a neutral overall charge. So the charges cancel each other out. We'll look to that in a future slide, though. Like charges, if I have like charges, 2 positives or 2 negatives, like for instance, 2 protons both with their positive charges tend to repel one another. 2 electrons, this is very important when we talk about chemical bonding. Electrons, because they both have the same charge, a negative charge, repel one another. So this is going to be raising its head more and more when we start looking at shapes of molecules and so on. The fact that some of these subatomic particles, the ones that are of the same charge, repel one another, opposite charges attract, and these are just the protons and the electrons. Now neutrons, since they don't bear an electric charge, do not attract or repel one another, or attract or repel protons and electrons from themselves. So let's now move to looking at how these subatomic particles are placed inside an atom. And this is always the case. It is known as the nuclear model of the atom, in which, as we see over here, we have our 3 subatomic particles, electrons, protons, and neutrons, showing their charges within there. We find that there are 2 essential areas to the atom, in the nuclear model of an atom. There is a nucleus, which is a very small, very dense area at the center of an atom. Understand that this is only a representation. Atoms actually don't look like this. We'll talk about a little bit more about the relative size of atoms compared to the size of our subatomic particles in a moment. But this is just a placement sort of thing. We see that all of the positive charge, meaning all of the protons, and all of the neutrons are contained in the center of an atom known as the nucleus, while all of the electrons I won't say orbit, but they move, they populate the area around the nucleus with electrons. So there's 2 essential places that we're looking here: inside the nucleus and outside the nucleus. And protons and neutrons are inside the nucleus, electrons are on the outside of the nucleus. So from a relative standpoint, let's look at the relative sizes of these things. So here is really a better way to express this is a very extremely small, extremely dense nucleus at the center of the atom, and then sort of this thin region outside populated by the electrons. They're not going necessarily in orbits like a planetary orbit around the sun, but that is a general way of looking at it. Now, the nucleus is surrounded by these electrons, nearly a huge volume of empty space, huge volume. So it's thinly populated with electrons, and it's important to note that there are the same number in an atom, the same number of protons in the nucleus as electrons taking up space outside the nucleus. Always the same number, and that is in order to cancel all of the charges on the protons and the electrons to neutral, so that they cancel each other out, so that an atom is overall a neutral entity. So let's look at some relative distances here. Here we have our nucleus, and if the nucleus was given as the size, if it was a centimeter, relatively speaking, if we could increase the size of an atomic nucleus, a standard atomic nucleus, to the size of 1 centimeter, that would mean that the boundaries in that region occupied by electrons would be 100 meters. 1 centimeter versus 100 meters, longer than a football field. So that is to show that virtually all of the inside of an atom, or all of the volume expressed by an atom, is empty space. Virtually all of it. So let's move back and talk about the sheer number of actual elements. We have said in the prior chapter that there are about 120 known elements. Now, each of these elements has a different atom. We learned that from Dalton's atomic theory, different type of atom. And what separates the types of atoms from one another are the numbers of the electrons, the protons, and the neutrons within them. Every different atom has a different number of protons, electrons, and neutrons. Atoms of the same element have the same number of protons and electrons. So if there's 120 different elements, we have to have a way of expressing these, or putting them together, listing them, if you will. And this is done by way of the periodic table of the elements, which is going to take some time in teasing through. Periodic table of the elements, we see here in this example of this, we have basically a lot of blocks put together. Different blocks. We have rows of blocks, and those are typically known as periods. And we can also look at elements with respect to columns, different columns of elements set on top of one another. Each of these is going to have its level of importance. So each of these blocks represents one different element. And we can see that these are all stacked together, put together into sort of a grid, but overall, the periodic table of the elements is written in a very, very strange way. We have sort of a main portion, which has a low point in it with two higher walls, if you will, of differing thicknesses. We have this sort of saddle piece in the middle. We also have this detached piece down here that we see here as part of the periodic table of the elements. We're not going to be going into the extremes in determining the shape of this periodic table, but we are going to be looking at a main portion of the periodic table of the elements. Now, I will say this it's a very busy sort of table right here. Not just because of each of the blocks within. We will be looking at, there's certain information for each element that we are going to be talking about, and it's identical in a periodic table for each element, or identical types of information. But also with respect to the periods, the rows, and the columns. I'm going to try to simplify our journey into the periodic table a little bit in saying that The periods here over on the left-hand side are of ultimate importance. Periods, are essentially correspond to the rows. Row 1, row 2, row 3, and so forth. And we find that some rows have very few elements in them. They're almost all empty space. This one has 2 elements in this row. The second row we find has a lot of empty space, but it has more elements. It has 8 elements within there. The third row has, again, shown here, 8 elements within there, and the fourth row, then finally the first row that they're all, every element box is in there. We don't have any empty spaces and so on. These periods, these rows are going to be of high importance. So let me show you what's not important. Look at the columns. Now the columns themselves are very important because we're going to be showing some reactivity regions of interest within the elements within these columns. But if you look at the numbering or the titling of these columns, 2A or 2 or what have you, it looks all different. It looks very complex. For this class, all of these column designations we are going to ignore. We're not going to be naming columns. I'm not going to be talking about, well, go to column 8A in the periodic table. I do not care. We'll be looking at them, some of them in a more sort of descriptive fashion, but the 2 different numbering systems we see on these columns are not important. So having said that, you'll notice, or we will find that we'll notice the area of the periodic table we're going to be spending the most time studying is on the upper end of things. So the sort of upper regions of the periodic table will be looking at elements in there much more often than, say, the elements in the lower portions of the periodic table, which we see here. Indeed, this cast off portion that we see right here, other than identifying it, we're not really going to be looking at any elements within there at all, at least with respect to how they fit into compounds and express in chemical reactions. It really is all of more of the elements up on top of the periodic table that are going to concern us. The reason is, at least for the models that we're going to project in this course, is because the reactivity of these elements in there are more predictable. They're more predictable. We like them better. If they're less predictable, then we have to keep coming up with exceptions to these rules. So let's look now at a representative depiction of a particular element. We're going to find that there are a number of different pieces of information in each one. Now, if we look at this, and we'll look at Be right here. Be is a chemical symbol, and it stands for the element beryllium. Be is beryllium. So those are 2 of the pieces of information within within each element's box, if you will, on the periodic table. But we also have some numbers. There's a number on the top, and it's always an integer number. That is the atomic number, also given as capital Z, the atomic number. In this case, the atomic number for beryllium is 4. Now, there's another number below the chemical symbol, and that is the atomic mass. It is almost always not in integers. It's in decimal form, almost always. We're not going to be looking at that. We're going to be looking at that towards the end of this unit of study, but we will focus more now on the atomic number than the atomic mass of an element at this time. Just understand that the placement is always the same. The atomic number is on the top of the chemical symbol. The atomic mass is on the bottom of that chemical symbol. So A couple of salient features about, again, we have beryllium here in a higher degree of relief, if you will, and it shows again the atomic number, the atomic mass, the chemical symbol, and the name of the element. One thing that we can say is that with respect to the atomic number, Z, that has special meaning. And it essentially says how many protons are in the atomic nucleus. Thus, for beryllium, has always, we know, the number of protons in its atomic nucleus is 4, always 4. And we find that the number of protons in an atomic nucleus defines the element. And the identity of an element is defined by how many protons there are in the nucleus. So again, for beryllium, it must have 4 protons in its nucleus. If it doesn't have 4 protons in its nucleus, it is not beryllium. It is not beryllium. So that's that top number right here. Now, again, the atomic mass we will look at in more detail later, but when we look at a periodic table, we're going to see some patterns in the layout of these elements with respect to the atomic number Z that we see in the layout of the entire periodic table. We'll be able to pick out some patterns and thus understand the periodic table in a little more detail. So there are many different versions of the periodic table, many different ways to express the information, some with all possible amounts of information, some missing some information. It really depends on the periodic table we're looking at here. Notice it has all of the important information, but in this case, it is one where the actual name of the compound is not put in, but the chemical symbol is. And as long as we're working with these enough, these chemical symbols will pretty quickly in our heads with repetition, we'll come to know them, their chemical symbols, and be able to identify the name of the element with them. Now, one thing, if we go back and look at the atomic number of an element, and specifically in this case, that, again, if you remember, that is the number that is on top of each of the elemental symbols that we see on there. And let's look at one way of reading the periodic table. Now, in this case, notice I have cast off completely that bottom part of the periodic table, the separated part of the periodic table. That's because, for the most part, we'll be working within the boundaries of what we see here, and specifically in the upper portions of what we see here, the elements in the upper portion of this of the periodic table. But let's take a look at this, and I'm going to ask you, or basically make a statement, because the periodic table can seem all over the place. It's like, why is it shaped like that? What are the significance of these numbers, and how are they put together? Is there any patterns that we can pull out of this? As we go through this chapter, or rather unit of study, and the next unit of study, we're going to find that the periodic table is laid out in a specific fashion, and that specific fashion, which may seem like haphazard right now, will make sense. So our first foray into that searching for patterns, if you will, would be as follows. And I say this sort of tongue-in-cheek, but when in doubt, read the periodic table like lines on the page of a book. So when we're reading the pages of a book, you know, we start on the left-hand side and read towards the right until we finish that line, and then we go to the line underneath it, start reading from the left, going to the right, and so on and so forth. If we do this, if we use this analogy with the periodic table, a pattern emerges. And that pattern is that the element's atomic numbers, the ones on the very top, will increase sequentially. So let's try that. That's this first row on the periodic table. There's only 2 elements in it, and we'll read it across, and notice that the atomic numbers go 1 to 2. Then we get to the end of that row, and we start the next row. And at the second row, we start reading across, and we count those atomic numbers: 3, 4, 5, 6, 7, 8, 9, 10. So we see this sequential increase. We're at the end of that row, and we start the next row, and it picks up right where we left off. 11, 12, again, going through a lot of empty space, 13, 14, 15, 16, 17, 18. Just like reading a book, go to that fourth row. And now, again, this is the first row in which all of the space is filled with these boxes of elements. And we can see that those atomic numbers on the very top are increasing sequentially. So here is the first pattern we see in the periodic table. It is the sequential increase, integer increase of atomic numbers with respect to as we read the periodic table like lines on the page of a book. Let's think back again. What does the atomic number mean? Well, it talks about, this is the number of protons that are in each element's nucleus. So now we can start to see that each element is laid out sequentially on the periodic table with respect to the number of protons in its nucleus. Each element is different because each number of protons is different. Each atomic number is different. Now, we will eventually address the seeming weird layout here. What's the story with all this empty space in some of these rows? What's going on here? Why does it suddenly pick up where there's a row where there's no empty spaces and continue with that? We will look at that. That's going to become more clear in the next unit of study. But what I wanted to do here is just to give a taste of the fact, or put the seed in your mind, that the periodic table, the layout of it is not haphazard. There is an important reasoning behind it, which will unfold more and more as we move along. So we perhaps saw one of the important characteristics of the rows or periods on the periodic table, in that if you read the rows like you do lines in the page of a book, what will open up to you is the fact that we get this sequentially increasing atomic numbers, which basically states the number of protons in each element's nucleus. Now, I've taken this periodic table and I've chopped it down such that the first 20 elements are in there. How do I know it's the first 20 elements? Well, if I read like a page, like lines on the page of a book, and go through this sequentially, I'm increasing in atomic numbers, that number at the top, continually until I get to 20. There it is, 20. Now, this may seem like sort of a strange way of expressing this, but I want to bring into focus now, we've looked at the importance of rows, periods, on the periodic table. Now I'd like to look at the importance of the columns on the periodic table, because the elements can be put into rows, as we see, but there's also vertical columns of elements in the periodic table. And this brings up a specific definition that I want to put across, and that is that definition, or that term, is periodicity. Periodicity, meaning periodically we encounter similar things. What that means is we have similar reactivity between elements in the same vertical column of the periodic table. What similar reactivity means, we have no idea at this point, because we haven't defined what reactivity is. So I'll ask you to allow me to take a little bit of license with that, other than to say we have some similarities here between the elements in the same vertical column of the periodic table. And since this is a chemistry class, I'm going to name those similarities with respect to reactivity. Fair enough. And we'll determine what reactivity is in a little while. Okay, so what if I took this sequential number of elements, and instead of putting them out on the periodic table on this fragment that I have here, what if I laid them all out in a line? If I laid them all out in a line instead, something like this. There's my 20 elements that I have here, and I've read the periodic table like lines on the page of a book, and I've simply put those all of those elements together in one long horizontal line. And you can see that because of the because of the atomic numbers on the top sequentially increasing all the way to 20. Now, another thing you're going to notice about this line of elements put in this fashion is that there's some color on many of them. Indeed, there should be some color on many more of them, but these are the important ones. And certain of these colors are the same. So here we have 3 in orange, here we have 3 in pink, and so on and so forth. What these similarities in colors represents is similarities in reactivity between the elements. Not identical reactivity, but similar reactivity. So what we can ultimately do now is set up the periodic table such that in rows, with leaving empty spaces in between if we need to, such that the elements with similar reactivity are right on top of each other in order that we can specify or put into language really what periodicity is. So watch what we do now. Now we've taken those 20 elements and we've set them up in this very rudimentary fashion in rows on top of one another, but in so doing, what we're able to do now is to put them in rows such that the colors representing similar reactivities between elements are now right on top of one another. And really what we see here is the nucleus of the periodic table. It's some of it. It is what it is the periphery of the periodic table. What we have, remember those 2 different thickness walls on either side of the periodic table. This one was over on the left-hand side, and this was over on the right-hand side, if you will. And we're missing what's in between. Essentially, though, we're starting to put this together with respect to how the periodic table is set up. This periodicity is an important consideration in the arrangement of these repeating columns in the periodic table now. These columns now have similar reactivity between elements. Again, not telling us what that similar reactivity is, but it is similar nonetheless. Again, some insight into why and how the periodic table is put together in the way it is. Once in the previous slide, we looked at that with respect to why the rows or periods are set the way they are, if we read it like the lines on the page of a book. And in this slide, why the columns are set together in such a fashion, and that is with respect to similar reactivity between elements in that same vertical column. So we're going to take a pause here, but stay on the general topic of similar reactivity between elements. And we find using the idea of similar reactivity between elements, the periodic table lends itself to certain detachment points, certain ways we can separate the periodic table into sections which in which the elements contained within these sections have similar reactivity, are governed by different types of forces, and so on. I'm purposely going to keep this, because we're early on in the process, keep this to a limited fashion. We're not going to be describing what exactly is the difference or the similarities between elements in these different ways of deconstructing the periodic table, but other than to just offer 4 different ways the periodic table can be broken up into different sections. Subsequent units of study, as we move forward, will cement these ideas together or uphold them based upon new information that we're going to be putting into how the periodic table is put together. But for now, it may seem just almost haphazard or random the way I am choosing these four following slides, or these four slides, to show detachment points of deconstructing the periodic table. But rest assured, as we move along, we'll be able to put these together and to utilize them and to understand why these different deconstructions make sense. Now, if we look at a periodic table and think about what are the most reasonable detachment points, we could there's relatively few. If we went through two detachment points, there are relatively few ones that we could do to come up with a series of blocks. And the first way of teasing apart the periodic table would be to label what is called the block nomenclature of the periodic table, the block nomenclature. And if we take our periodic table and we cleave it in these two spots, well, we really have four almost square blocks. And these blocks, first of all, have letters associated with them. There are lowercase letters. The one over here on the left is known as the S block. The one that's low saddle in the middle of the periodic table is known as the D block. Over on the right-hand side, this thick wall, if you will, is known as the P block. And the section we're hardly ever going to be even looking at, that detached section that's already detached from the periodic table in any periodic table that you look at, that would be the F block. So that is the block nomenclature of the periodic table. Now notice one thing, it seems like we have sort of one of these things is not like the other here. We have this pink box over here, which actually corresponds to the element helium, and we have a spot in the pink S block where that pink block over on the P block could sit. And that is because the first row or period on the periodic table has a lot of contradictions to it. Indeed, this the placement of this, there are periodic tables where the placement of this number 2 that we see over here block occurs on the left-hand side and it occurs on the right-hand side. Most of the time we see that element helium over here for a reason we'll be looking at in the next unit of study, but it actually, in many ways, contradictorily, belongs over here to finish out the S block. I typically don't like to present contradictions in the models that I show in general chemistry in this class at this level of play, but it is compelling, and we're going to see that as we explore more and more the layout of the periodic table, we'll start to see and sense that that dichotomy between the placement of these of this sort of seemingly misplaced pink block here. The next way of deconstructing a periodic table is not sort of this, to put it into blocks, these nice 90-degree angles, but it allows us to discern on the periodic table between what are considered metals and what are considered nonmetals. Metals and nonmetals. Now, on any periodic table, you'll notice what is called the stair-step line. That stair-step line is a diagonal line. In many cases, it is more pronounced than others, but we see it right here, and it is a diagonal 45-degree angle down sort of stair-step, if you will, which separates what are considered metals from what are considered nonmetals. Now, the metals are the elements within this this area right here in the periodic table, in the northeast quadrant, if you will, the upper right-hand side. These are all considered nonmetals, whereas the vast majority of the periodic table is considered to be made up of metals. So we have metals versus nonmetals in the periodic table. Now, there's also, in this stair-step line, there are elements that are hugging that stair-step line, and they are a different color here. If you look very, very closely, we see that we have these purple colors within these elements, many of these elements that are hugging that stair-step line. We are not going to be considering these. These are normally considered metalloids, meaning they have properties comparable to metals as well as nonmetals. It gets too complicated. So I'm just going to be looking at this stair-step line, at least for this class, and anything up on this area are metals, anything in this, I'm sorry, are nonmetals, anything in this area are indeed metals. Thus, if on a test or a quiz or an exam, I were to ask you metal or nonmetal, I would never pick one of these purple ones, because technically they're a metalloid, and if you said, no, well, they're neither, that could be considered a correct answer. So what I do, if I said, well, which is a metal, which is a non-metal, you know, I'd pick something well within the non-metal range or well within the metal range, and that's what you would be given to ultimately choose from. So what is it really that separates metals from nonmetals from how can we discern them from one another? Well, there are two ways. One is more chemistry based and one is more colloquially based. The first is that we can say that one of the differences is that metals tend to lose electrons in chemical reactions, while nonmetals tend to gain electrons in chemical reactions. Because we're not talking about chemical reactions yet with respect to electrons, that's not going to make a lot of sense. It will eventually when we start talking about how electrons, the dance of electrons essentially means we're talking about a chemical reaction happening. But for now, metals tend to lose electrons in chemical reactions. Non-metals tend to gain electrons in chemical reactions. So that's more of something with a chemistry bent to it. A more sort of general way to look at it would be that metals tend to conduct electricity, while non-metals do not conduct electricity. When we start talking about chemical bonding, metallic bonding, we're going to see how metallic bonding lends itself to the conduction of electricity, whereas nonmetals do not. Nonmetals, many of them are useful as insulators. They don't conduct electricity, therefore they can be used as insulators when we're working with electrical current. The third way of deconstructing the periodic table brings us back to those nice vertical lines again, into vertical blocks. And indeed, notice we're just looking at that partial, the major component of the periodic table, while leaving off that cast-off piece, the F block below. And in doing so, we are now able to discern between what are called the main group elements versus the transition elements. Notice that the main group elements sort of comprise these walls of the periodic table. Here's the walls that we're looking at right here, not that saddle piece, that low saddle piece inside. That is considered the transition elements. So we can essentially say that our main group elements comprise the S and the P blocks that we looked at our first example of teasing apart the periodic table, whereas the transition elements comprise what was the D block. How to discern between them is basically an unscientific way of doing that. But if you look down at the bottom here, my definition of the difference between them is that the chemical reactivity of main group elements that we see in yellow here, I claim is more predictable than the chemical reactivity of the transition elements. Now, that's not necessarily true. When we talk about predictability and reactivity, we have to talk about adherence to a particular model of reactivity. The model of reactivity that we're going to be discussing in this course only applies to elements within the main group, or if you like, within the S block and the P block. A different model applies to elements within the transition elements, so we can say, from a more general standpoint, that the transition elements, their reactivity is less predictable. Is less predictable than the chemical reactivity of the main group elements, which makes sense because we're only going to be developing a model which is specific for those main group elements. And the last way, the last method of deconstructing, teasing apart the periodic table would be sort of bringing this from the previous slide. It's just basically bringing the main group, some of the columns, specific columns within the main group elements, giving them essentially colloquial names. So let's look over on the left-hand side, part of the main group elements. We have a couple of columns here that that we have colloquial names for. The colloquial names are ones that are sort of lost in history. They've just sort of always been the case. So they've endured, if you will. Don't really have a specific scientific basis for naming them, but they have endured. So the first column, if you will, over on the left-hand side, really is known as the alkali metals. Really are encased in these pink ones right here, not hydrogen. See, we see the element hydrogen right here. But as we know, the first row of the periodic table is fraught with sort of exception, if you will. So that's where hydrogen starts. It's not considered an alkali metal by itself, but the ones below it are. That we see that I've circled right there. These are considered alkali metals. It is important that it is alkali metal, that we don't call them alkaline metals. That would be wrong. Which brings us to the next column over on the left-hand side, if you will, and these would be the alkaline earth metals. Alkaline earths are the ones we see right here. Alkaline earth metals. They are both. These columns are metals. They are within that metal area within the periodic table, but they're called alkaline earth metals. Taking a journey all the way over onto the other side, to the right-hand side of the periodic table, we can see that the farthest one over on the right-hand side are known, that column are known colloquially as our noble gases. Why they are considered noble, we'll talk about with respect to their reactivity, or rather lack of reactivity, at a later point. The column, which happens to be right next to the noble gas, is that of the halogens we see right here. Halogens. Our halogens include the fluorine, chlorine, bromine, iodine, and so on. Whereas our noble gases have helium, neon, argon, krypton, xenon, and radon within them. So within our main group, if you will, we have we have certain colloquial names for certain columns. There are other names for particular columns, but they are used so infrequently that it's not really that important that we express them here.